Hello, today we are continuing our GCSE physics revision series looking at work and energy. If we have a mass, m, on the floor, and we push it with a force F through a distance d, so we push it from here to here, then the work done, as far as physics is concerned, is simply equal to the force times the distance. Please note that the force has to be in the same direction as the distance that you're going to push it through. If the mass is here like this on the floor and you push down on it at an angle with a force F, the work is not force times distance because you're not pushing wholly in the direction that you want to go. We'll talk about how you resolve this a little bit later on, but for the time being, this formula applies when the force and the distance are in the same direction. In other words, you're pushing in the direction that you want to go. Or pulling. It doesn't matter. Let's suppose that we have a cart and I am going to pull that cart and I am going to exert a force of 400 newtons as I pull the cart, and I'm going to pull it a total distance of 10 meters. What is the work done? The work done is force times distance. I'm okay because I'm pulling in the same direction as I want the cart to move. Work is force times distance, which is 400 newtons, that's the force, times 10 meters, that's the distance. So that's going to be 4,000. What are the units? Well, the units of force are newtons, the units of distance are meters, so it's 4,000 Newton meters, but we have a special name for work, and that is joules. So a joule is a Newton meter. Work, as we shall see, is essentially a measure of energy, and therefore joules are also a measure of energy. Let's talk about kinetic energy. Kinetic energy is what you get when you have something moving. Kinetic energy is a half mv squared, where m is the mass and v is the velocity. So if we have a mass m moving at a velocity v, remember velocity is a vector, it has a direction, so the velocity is in the east direction, then the kinetic energy is simply given by this term here, half mv squared. By contrast, there's a thing called potential energy. Potential energy because it has potential to do something. If I have, here is the floor, and I have a mass m, and that mass is at a height h above the floor, the potential energy is given as mgh, where m is the mass, g is the gravitational attraction that we've dealt with before. On Earth, that's 9.81 meters per second squared, and h is the height above the ground. What we're saying is that if you hold a mass a distance h above the ground, it has potential energy. Why? Because if you let it go, it will fall to the ground, and in falling to the ground it will gain kinetic energy because it will speed up as it falls, and when it finally hits the ground it will be travelling at a certain velocity. It will have a kinetic energy. And potential energy can convert into kinetic energy. Let's consider a cliff. And on the edge of the cliff, precariously balanced, I have my mass m. The height of the cliff is h, and I am standing next to the mass, ready to just gently push it off. The potential energy of that mass, we've already said, is mgh. The mass times the gravitational attraction g, 9.81, sometimes you can use 10, and the height of the cliff. Now, suppose I were to push that mass over the edge so that it now falls until it hits the ground below. When it gets to the ground below, its potential energy will be mgh again, but now h is 0, because h is the height above the ground, and when it hits the ground, h is 0. So the potential energy when it gets to the ground is 0. Where has that potential energy gone? Energy can be neither created nor destroyed. What has happened is that potential energy has been converted into kinetic energy. So when it hits the ground, the kinetic energy will equal a half mv squared. Consequently, what we can say is that potential energy has become kinetic energy. It's all been converted into kinetic energy. So mgh, which was the potential energy, has equaled a half mv squared. Let's do a sum. Let's suppose that the mass is 10 kilograms, and let's suppose the height is 10 meters. I'm doing this just to keep things simple. And let's suppose that g, which is normally 9.81, let's suppose we've been told that we can regard that as 10 meters per second squared. What is the velocity when the mass hits the ground? Well, we've got that the potential energy was the mass times g times h. The mass, you remember, was 10 kilograms. The gravitational attraction, we were told we could use 10. And the height above the ground was 10. So that's going to be equal to 10 times 10 times 10 is 1,000. And the units, remember, of energy are joules. And those 1,000 joules have been converted when the object reaches the ground. So it's 1,000 joules of potential energy. When it falls to the ground, that converts entirely into kinetic energy. And so that 1,000 joules now becomes half mv squared. So half mv squared equals 1,000. A half of m, well, m, remember, was 10 kilograms, so half of that is 5. So 5v squared is equal to 1,000. And if we divide both sides by 5, we get that v squared is 200, and the square root of 200 is of the order of 16 meters per second. So when that block falls off the top of the cliff, by the time it hits the bottom, assuming no air resistance at this stage, so no terminal velocity, it will achieve 16 meters per second. Of course, bodies can have potential energy and kinetic energy. Let's suppose that this is the Earth, and here is the atmosphere around the Earth, and here is a meteor. And that is moving towards the Earth, being maybe attracted by the Earth's gravitational attraction and destined to land on the Earth. That meteor is moving, it has velocity, so it has kinetic energy of a half mv squared. And of course it is a distance h above the Earth, so it will also have potential energy. It won't have potential energy of mgh, as we might think, because of course, as we showed earlier, the value of g varies, indeed it reduces, the further you get above the Earth. G equals 9.81 only really applies if you're on or fairly near the surface of the Earth. So you need another formula for potential energy, which we don't need for GCSE, but it certainly will have a potential energy and a kinetic energy. So we'll just put PE for potential energy and half mv squared for kinetic energy, and all that energy is going to be coming towards the Earth, and were it not for anything else, when the meteor hit the Earth, there would be a pretty big bang. But of course what actually happens is as the meteor enters the Earth's atmosphere, it will hit the atmosphere itself. There will be air and there will be air resistance. And that air resistance will cause the meteor to heat up. And indeed, in many cases, to burn up. And that's what you observe when you look up in the night sky and see a shooting star. That's exactly what you're seeing. A meteor entering the Earth's atmosphere and burning up. Either entirely or in most cases to leave only a small amount of remains to land on the Earth. There is a thing called elastic potential energy, such as the energy that is in a spring. If we take an ordinary spring, we can do two things with it. We can either squash it so that it is pushed together, or we can pull it so that it is expanded. And in either case, we would have to hold on to the spring because it would have potential energy. If I let go of this coiled spring, boing, it will spring out. If I let go of this extended spring, boing, it will contract. Hidden in the extended or the contracted spring was energy. And that energy is released if you let go of the spring and for example, if I put something in the way here, it would knock it out of the way. It would have the energy to be able to hit it. If you take a spring, an ordinary spring, suspend it from something, then it will have a natural, as it were, length. If you hang a mass on it, the spring will extend to a new position. And there will be an extension of that spring, which we'll call E. And the force that you need to extend that spring is given by K times E, where K is what is called the spring constant. But the force that you apply will determine the extension. The greater the force, the greater the extension. What is the force if I hang a mass on a spring? If that mass is m, then we know that the force that is applying is a force downwards of mg. That's the weight of the mass. And consequently we can say that mg is the force and that equals ke. Now g is a constant and k is a constant. K is the spring constant. So mass is going to be directly proportional to the extension. The greater the mass you put on the spring, the greater will be the extension. So this is, in a sense, a way of measuring mass. You simply have to calibrate your spring by putting known masses on and determining where the extension is. And then you can use any mass. So you would essentially have a graph where you would have the mass or the force of course is just equal to mg along this line here, and the extension here, and you would get a straight line graph, so that if you put a mass on that you didn't know and it happened to give you an extension of this amount, then you just go up to the graph and read across, and that tells you what the force is, and therefore, since force is mg, what the mass is. So here's a means of measuring mass simply by the extension. But the spring will have limits. You can't, for example, find the mass of an elephant on the spring. It's certainly true if we draw the force, which of course is equal to mg, versus the extension of the spring, it is certainly true that for a reasonable force, you will get a straight line. So you can always measure the extension and thus work out what the mass or the force is. But if you try and put an elephant on the spring, of course, what will happen is you'll see something like this happen, and at that point, you go beyond what's called the limit of proportionality. Here, you've got a straight line proportionality which says that the extension is directly proportional to the mass. But after you put too heavy a load on, that is no longer a straight line, and the reason is that the spring is no longer behaving itself as a spring should. When a spring is extended, if you release it, it should go back to its original shape. But if you put too heavy a load on it, it will just distort out of shape, and when you take the load off, it won't go back. You will for all time have distorted the spring. So once you get past the limit of proportionality, the spring is probably broken and you can't use it anymore. Let's now just do some typical problems that you might get in your exams about work and energy. Suppose I have a 1 kilogram block and I want to put it up onto a table which is 2 meters tall. What work will I have to do to lift this block up onto this table? Well, you'll remember that we said that work is force times distance. That means that work is going to be the force, which is mg, so that is going to be 1 times g, and g I'm going to say you can regard as 10 meters per second squared. Quite often you'll be told you can do that. Otherwise you have to use 9.81, which is a lot more difficult. So that's the weight, the mass times g, 1 times 10, and d of course is just 2 meters because that's the height of the table. And so we're going to get that the work is 1 times 10 times 2, which is 20, and the units of course are joules. You'll notice that that is the work done, but it's also the gain in potential energy. What is the potential energy of the mass when it's on top of the table? Well, when that mass is on top of the table, it will have potential energy equal to mgh. And m was 1 kilogram, g we said was 10, h was 2, so that's 20 joules. And that makes sense. You had to do 20 joules of work in order to give the block 20 joules of energy. Now the second part of the question, suppose the block, which is now on top of the table, falls off and hits the floor. What is the velocity with which it hits the floor? Well, we know that it had PE, a potential energy of 20 joules. When it falls off the table, when it hits the floor, the potential energy will be 0 because mgh will be 0 because h will be 0 because h is the height above the floor, and when it's on the floor there is no h. It's all been converted into kinetic energy. The kinetic energy is a half mv squared. So that 20 joules of potential energy has been converted into kinetic energy. So a half mv squared is equal to 20. M, you'll remember, was 1 kilogram. So this is essentially v squared over 2 equals 20. V squared equals 40. And v is the square root of 40, which I think is 6.32 meters per second. So when that 1 kilogram block falls off the table, 2 meters up, smashes onto the floor below, when it hits the floor, it will be travelling at 6.32 meters per second. Here's another problem. We have a car which has a mass of 200 kilograms and it drives a distance of 200 meters. And its acceleration, as it does that, is 1 meter per second squared. First part of the question is, what is the driving force of that car? Well, force, we remember, Newton's second law, is mass times acceleration. That is going to be, mass is 200 kilograms, Acceleration is 1 meter per second squared, so that's going to give us 200, and the units of force are newtons. So the driving force of the car, effectively the force provided by the engine, is 200 newtons. We're forgetting about air resistance and friction for all of this. Second part of the question, what is the work done by that car in travelling over those 200 metres? And we remember that work is equal to force times distance. And the force we've just calculated is 200 newtons. The distance was 200 metres. So now the work done is 200 times 200, which is 40,000 joules. Or, let's see if I can get that on, or you can write that as 40 kilojoules, where the K is essentially 1,000. So 40,000 is the same as 40K. Then we're told that when this vehicle gets to its top speed, it has an energy, a kinetic energy, of 100,000 joules. That's when it's travelling at its top speed. And we then apply the brakes, and the brakes have a braking force of 2,000 newtons. So the car has reached its top speed, its kinetic energy is 100,000 joules, and we apply a braking force of 2,000 newtons, and the question is, how long does it take the car to stop? Well, we have got to do work to take that kinetic energy away. So the work will equal the kinetic energy, and that equals force times distance, because work is force times distance. So the kinetic energy is 100,000. We've given that. That's here. The force we know is 2,000 newtons. We were given that. The only thing we don't know is the distance. So the distance is going to be equal to 100,000 divided by 2,000, which is 50 metres. So it will take 50 metres for that car to come to a halt if it starts with 100,000 joules of energy and you're applying 2,000 newtons of braking force. Here's another question. A car is travelling along the road. The car has a mass of 200 kilograms and it's travelling at a speed of 10 meters per second. What is its kinetic energy? Well, that's fairly straightforward. Kinetic energy is a half mv squared. So that's going to be equal to a half times m, which is 200, times v squared. Well, v is 10 meters per second, so v squared is 100. So that is going to equal a half times 200 is 100, times 100 is 10,000 joules. So the kinetic energy of that car is 10,000 joules, and as we said, you can also write that as 10 kilojoules, because the K represents 1,000, so 10,000 is the same as 10K. Here's another question. We have part of a roller coaster. The part where the car gets pulled up until it gets to the top and then it begins to come back down again. And we know that we've got a little car. I need to move this over a bit. So we've got the little car, and that is going to be 500 kilograms, and the car is going to be pulled up by some kind of motor to the top, and then it's going to be allowed to run down the other side. So I can tell you that we will always take g to be 10 meters per second squared. So the first part of the question is, what is the work done? I can tell you that the top of the roller coaster is 10 meters above the ground. What is the work done in getting this little car all the way up to the top? That's the first part of the question. Well, work done, as we know, is force times distance. And the force is not, of course, 500 kilograms, it's mg. So that's going to be 500 times 10, that's mg, times the distance. Now, here's the important thing. When we talk about distance, we do not mean the distance along the track. We mean the vertical distance. It doesn't matter how you raise something to a vertical distance, whether you go directly upwards or whether you go at an angle. It's the vertical distance that matters. So the distance in this case is 10 meters, the vertical height above the ground, not the length of the track. That sometimes can be a bit of a trick. And 500 times 10 is 50,000 joules. So you're going to need an engine with 50,000 joules of energy to get that little car to get to the top of the roller coaster. When it is at the top of the roller coaster, of course, it will have a potential energy of 50,000 joules because the work done has provided the 50,000. The potential energy when it's at the top equals mgh, and that's going to be, mass is 500 kilograms, g is 10, h is 10, that's the height, 10 meters, and that equals, of course, 50,000 joules. That's entirely reasonable. You did 50,000 joules worth of work to get the thing to the top. It then has 50,000 joules worth of potential energy. Now, of course, in practice, we are only talking about theory here. In practice, the motor that you would use to pull the car to the top would have to have more than 50,000 joules worth of energy, because some of that energy is going to be wasted in reality on friction and heating as this car is pulled up the track. So it's not going to be a case of being 100% efficient. You're going to lose some of that energy in the form of friction and so on. So the engine will always need to be at a higher rating than the actual work done in purely theory considerations. Part 2 of the question is we then let the car which has got to the top of the track run all the way back down again to the same level it started. And the question is, when it gets to this level here, what is its velocity? Well, once again, we know that the potential energy that it had at the top will be converted to kinetic energy, which is a half mv squared. So it had 50,000 joules of energy at the top, and that's going to equal a half times m, which is 500, times v squared. And that's going to result in v squared equaling 200. Because you've got a half of 500 is 250. Bring it on this side, you have to divide it. 250 into 50,000 is 200. And that gives you, if you take the square root of 200, you get 14.14 meters per second. So when the car gets to the bottom, it will be travelling at 14.14 meters per second, provided it is true that all the potential energy is converted into kinetic energy, which for the purposes of this question it will be. In practice, of course, it will again lose some energy by friction as it comes down the track. So these are all theoretical predictions. In reality, it would not be as simple as that.